Okay, good morning. So in this exercise, validating sets of quantum numbers, we have to understand the parameters that each of them has. And I asked just now, are you analyzing from left to right, or are you analyzing from right to left? It actually doesn't matter, but you do need to know that relationship, n, l, m sub l, m sub s, and then the relationships they have with each other. What is the only invalid answer for n? Jacob? 0. I guess actually we could expand that and say any negative number. Yes. But according to our periodic table, there is no zero energy shell. There is a first energy shell and then higher. On our periodic table, what is the highest value of n? 1, 2, 3, 4, 5, 6, 7. There you go. Not to say that that is the highest valid number for n. It goes to infinity. Okay, how is L defined according to n? Jacob again. Good. From 0 to n minus 1. Is 1 between 0 and n minus 1? N minus 1 is what? N minus 1. Here, that gives us 1 minus 1. That equals 0. So this set is not valid because of L. Otherwise, 0 would have been a valid m sub L for 1, and plus 1/2 is one of the two valid m sub s. All right, somebody walk me through the second set. Right.
So we got n equals 3, which is totally fine. Right?
Good.
And then our next one is n minus 1, so 2 totally works out there. And then that one, we got our bound, so from -2 to +2, it falls in there, so
Good.
that works. And then the spin being -1/2 works as well, just because it's either -1/2 or
Good. Now this one was entirely coincidental that I went 3, 2, 1, -1/2. It could have also been 3, 0, 0, -1/2, or 3, 1, -1, 0, +1. It could have been 3, 2, -2, -1, 0, +1, +2. Because the constraint on m sub L, like Ryan said, is from -L to +L, and 1 falls between -2 and +2. Okay, so this set is valid. What about this third set? Anybody? 0. The answers are valid or invalid? Invalid because of?
The gross 0.
Okay, so spin must be +1/2 or -1/2. So if you're working your way from the left, you might have missed this easy reason to throw out this set. M sub s has to be -1/2 or +1/2. But also,
The 3.
L is larger than n, not between 0 and n minus 1. So there are two reasons why this set is invalid.
So you could have a set where n equals 7 and L is 0, and that function would be valid?
100%. N is just the energy shell that you are in. Predominantly, how far away from the nucleus are you? But L is the angular momentum, not the spin, which is confusing. L being the angular momentum says, does your electron's region look like this? Is it just round? Does your electron region look like this? Does it have two regions where the math changes sign? What is that region we call where the math changes sign? Where we find the electron 0% of the time? A node. This is a node where the math changes sign from plus to minus. So if you are in, Lizzie, n equals 7, you have an orbital that looks like a sphere, 3 orbitals that look like these propellers, 5 orbitals that look like this, 7 orbitals that look like F, which is just more complicated. You also have the potential to go higher beyond F, because L equals 0 is the circle, L equals 1 is P, L equals 2 is D, L equals 3 is F, you have the potential that an electron in the 7th energy shell, on our periodic table at the bottom, has L equals 6, or L equals 5, or L equals 4, which we're not even giving names to. But it would go F to G to H to I. But they're theoretical at that point because they're not being filled. Good question. Okay, last one, valid or invalid? Jordan, why is it invalid? Good.
Because that's lower than the -2, which is about outside of our constraints.
The valid options were -2, -1, 0, +1, and +2. But -3 falls out of that range. Good. N equals 4, valid. L equals 3, valid. I'm sorry, L equals 2, valid for N equals 4. But M sub L equals -3, not valid for L equals 2.
I thought for L it had to be between. It would be 0. Oh, okay, never mind.
L has to be between 0 and N minus 1. 0, 1, 2, and 3 are all valid here. Great work. All right. We left off last week talking about M sub L and showing how for different L values, you have a different number of M sub L values. When L equals 2, you have 5 M sub L values. When L equals 3, you have 7 M sub L equals values. But when L equals 1, when L equals 0, which is our sphere, you only get 1 M sub L value. The only other thing we didn't touch on was M sub S, which is that spin of the electron. And there are two values valid, +1/2 and -1/2. And I put spin in quotation marks here because an electron being both a particle and a wave, it might be easy to think of that particle nature spinning like a basketball, but it's a wave, so it's not really spinning. So imagine that the electron is a ball and is spinning, but it's not a ball and it's not spinning. That's what M sub S is telling you. Okay? So I want to do this. I want to take all of the electrons that we can have for an element and describe how those electrons are configured. These are electron configurations. How are the electrons that an atom holds distributed? That's what we're communicating. We know how to calculate the number of electrons, correct? You look at the charge on an atom. If it's neutral, electrons equal to the number of protons. If it's negative, there's an excess of electrons. If it's positive, there's an excess of protons. We want to say now, how are those electrons distributed? What energy shell are they in? What suborbital are they in? What subshell? What type of orbital? Which specific of those orbitals? Is that electron spin up or is that electron spin down? We have two rules that we need to follow here. The first rule we're going to follow is the Aufbau principle. You want to say it louder, Ryan? Aufbau said. Good. Just like if you are throwing balls into a ball pit, you will fill from the lowest energy to the highest energy. You're just going to fill from the ground up. That's Aufbau's principle. From lowest energy to highest energy. This is the ground state. All of the electrons are as low as they need to go. Which electrons go where? Doesn't matter. There's enough of them. They have to go somewhere. They're going to go somewhere from lowest to highest. And the second rule that we'll follow here is the Pauli exclusion principle. What did Pauli say? It's exclusive. Kind of, yes. No two electrons can share all four quantum numbers. That is to say that if you have an electron occupying the first energy shell, the s orbital, then there can't also be another electron in the first energy shell and the first orbital. But that's not true. There are two electrons there, which is, again, where m sub s comes in. The first electron is spin up, plus 1/2. The other is spin down, minus 1/2. Now they have four unique quantum numbers. But no two electrons can occupy the same four quantum numbers. Quantum numbers are trying to tell you something about the electron, so you can think of it similar to each of you being in your seats, right? There are multiple of you in specific rows, similar to being in specific shells. There are multiple of you in these groups, similar to being in subshells, p orbital types, but you're each in your own chair. So you're each distinct from each other, except electrons go one weirder, where one of you can sit in the chair upright and the other can sit in the chair upside down, and then you both occupy that chair. Not as clear. But again, electrons are weird things. Okay, so here's what I want to do. I want to take magnesium, and I want to write the electron configuration. Instead of just giving a list of N, L, M sub L, M sub S, we're going to condense some of that together, and we're going to write it as kind of a sentence. Instead of L, we'll be using the letters S, P, D, and F. But first I need to know, how many electrons does magnesium have? Okay, I heard two answers, and both are good to start with. One said 10 and one said 12. You want to clarify?
Yeah, so basically it can have both, but if it doesn't have a charge, it would be 12, but if it has a charge, then that's
Got it. You got it.
And is it magnesium only +2?
But is it written as +2? What is it written as? Magnesium neutral. So how many electrons do we have to work with? An even number to the number of protons, 12 electrons. Good. Where do those 12 electrons go? Well, they go to the first energy shell, which is the lowest energy shell, correct? And in the first energy shell, there is only one subshell, the s orbital. So we say 1s. And how many electrons can that s orbital hold? 2. So we designate this number of electrons in this subshell as an exponent, a superscript, to differentiate it from the coefficient n. 2. 1s2. Now my first shell is full. My first shell only holds 2 electrons. So I've gotten 2 of my 10 electrons in. I move to the next energy shell. Second energy shell, this is N. The first subshell is again S, and this can hold 2. And then I go in my second shell to the next subshell, which is P. And how many electrons can 2p fit? Good. And if you need a reminder, your periodic table tells you 1, 2, 3, 4, 5, 6 electrons can go in the p subshell. All right, let's check in back real quick. 2, 4, do I have 6 to go? I do. So I can fit all 6 of them in there. Now I have how many electrons left over? I still have 2. They need to go in the next lowest energy, which is going to be the third shell. How do I know that I'm done in the second shell? Well, n equals 2 has 2 valid L numbers. L equals 0 and L equals 1. And those have different sets of M sub L numbers. M sub L equals 0, M sub L equals -1, 0, and +1, each holding 2 electrons. So I'm done because the second shell can't have another L. I need to go to the third shell. And what's the lowest subshell? Good. S, 1s2, 2s2, 2p6, 3s2. And I'm putting both of the electrons in there that I have left. That's my electron configuration. Which of the 4 quantum numbers does the electron configuration not clarify? Spin. +1/2 and -1/2 is not clarified. Also, I guess to be fair, M sub L is not clarified. I'm not telling you which of the 3 p orbitals these electrons are going in, although I guess since it's filled, it's going in all of them. So M sub L, M sub S, not really clarified. But N, L, and number of electrons there used as exponents. What would come after 3s2 in terms of available orbitals? 3p comes next. We could, in theory, say that magnesium has 3p0 electrons. Sorry, would it help if I gave you the whole table? We skip over this whole block. But I do want you to pay attention. 1s2, 1, 2, 1s is done. 2s2, 1, 2. 2s is done, but 2 is not. 2p6. These electron configurations are reading the periodic table until you get to your element, your atom. But then, of course, if you have charges, you need to backtrack by whatever amount. We could have said 3p0. What would come after 3p0? That's what the periodic table says. The periodic table says 3p0 go down to 4s. But we know about 3. N equals 3. L equals 0, 1, and 2. What type of orbital is 2? L equals 2. It's not S. It's not P. It's D. So why is it that we don't find 3D? We find 4S. Then what do you suspect this D block is? 4D? It must be 3D. So we are filling in lowest energy first, but at this tipping point of 4S and 3D, energies tip to become less intuitive. It's not just the next in the shell. You can skip the third shell, D subshell, to move to the fourth shell, S subshell. And I have another GIF for you on this, or a reel, I mean, boomer. Honestly, this would have been a better meme if it said electron configurations after 3p6, looking at 4s versus 3d. Because, well, I guess because he actually goes in this guy's hands. This is the weird thing, is that the electron prefers to jump into a higher energy shell rather than completely filling the energy shell that's being filled at the moment. That's where you guys need to pay attention. Okay. Questions on that? No?
Do we know why?
Yeah, actually, it's kind of represented here. It's just energy levels. There is, like if you calculate the energy difference between 4s and 3d, surprisingly, 3d is a higher energy. And maybe it's just the way the math works out. We have kind of set these lines to say here is a quantum shell, n equals 3, and then that becomes intuitive to think that will be a lower total energy set than the next quantum shell, and it just doesn't. It's allowed to break, I guess. Yeah? Yeah. Okay. Sorry, I'm just doing this to try and get some white space on the board. That's not what I wanted, though. These electron configurations can get kind of long and cumbersome. So we introduce condensed electron configurations where we can abbreviate a whole set of electrons with the nearest noble gas. Maybe instead of nearest, I'm actually going to say most recent. And we're going to put that noble gas into these brackets. By using a noble gas, we're saying, look at this noble gas. All of its electron shells are filled. From that noble gas's configuration, we add these electrons to get to our element. So can someone pick a new element for me other than magnesium? Keep it above like the 5th row. Iron? Let's look at the electron configuration for iron. So we'll have to trail back to our left on the periodic table and then find the most recent noble gas above that. Here's iron. The most recent noble gas was in the 3rd row, argon. So we say that iron's electron configuration resembles argon, but also has, reading the periodic table, that's 4s2. Before we go back and start filling what? 3d. And how many electrons in the 3d? To get to iron? How many electrons can fit in the 3d subshell? 10. 2 in each of the 5 orbitals. So does iron have a filled d subshell? No. It's coincidental that you're seeing 6, which is when p is filled. But this is just 3 of the 10 possible spots. Can you guys give me nickels? Nitrogens. Thinking metals. Nitrogens condensed electron configuration. What's the most recent noble gas? Helium. Not saving ourselves a lot of work, are we? And then what? 2s2, because that's 2s block is filled. 2p3. There you go. All right, now can you determine, well, let me just give myself a hand so I don't give you something wrong. No. Can you determine this electron configuration? Can you figure out the element that is represented by this electron configuration? You have it already? Good. Krypton, 5s2, 4d10, 5p5. Just raise a hand if you think you have the element. Okay? Good? That's good. Thank you. Not yet. Anybody want to share from this half of the room? I'll wait to see. Anybody want to share what's holding you back from identifying it? Daniel?
I'll say the total number of electrons.
The total number is holding you back? Okay. How many electrons in Krypton? 6? 36. Plus 2, plus 10, plus 5. So that's 46, 48, 50. So it should be element number 53? Iodine. Did that actually work? We can just add up the number of electrons, if it's neutral, to find our element.
You can just skip that though and keep following along if you have the periodic table. You don't necessarily have to do an extra math.
Correct. You don't have to. That would be a good proof, though. Here's what I would have done. I would have started with Krypton and recognized it's nothing above that. And then I would have realized I'm not in the D block. I'm not in the S block. I'm somewhere in this P block, specifically 1 electron away from being filled. 5p5, that's almost 5p6. That's just 1 electron short of being a filled 5p6 iodine. Good. All right. Ashley.
So would you ever be able to tell the downspin or upspin of just this?
Good question. No. You cannot use electron configuration to determine upspin, downspin, or even like which orbitals, right? But here's something we can do. I'd like you guys to take 1 minute with a partner to come up with a valid set of quantum numbers for any of iodine's 53 electrons. We know that iodine holds its electrons in these shells and subshells. So now I want you to come up with one valid set of quantum numbers for one of the 53. It should be feasible if every single one of you did your own for us to have completely different sets and describe completely different electrons. But I'll have you work in pairs or groups. Come up with a valid set of quantum numbers. And then if you're feeling brave, come put them on the board.
And then I subtract 0, 0. Figure out 0. It can be 4, it can be 3, 2, 1. But if we make it 0, then everything else is 0.
just a list.
That works. So basically, just take the first number that you use, do it.
L equals 4. Do you, L equals, this is a valid set, but it's not one of its electrons. L equals 4 is not even F. L equals 4 is above an S shell.
Oh, so it'd have to be like 1 or 2 then.
Correct. 0, 1, or 2.
0, yeah.
But actually, but not 2, because that would be 5D. And we see from its configuration that it only has electrons in the 4D.
Okay, that makes sense.
I'm going to explain that one, though, too,
Yes,
So
when you're done.
leave it?
No, go for it. Because, great, much better. Can I get 3 more on the board? And they do not need to start with 5, by the way, just in case that is throwing you off. Those are all coincidentally in the same shell, but they do not need to be in that shell. Iodine has 53 electrons. That means 53 individual quantum number sets. Come on, 3 more.
So technically it could be like 52.
I'll write it. I can write it.
There are 53. There's 50 more.
Okay.
There's 50 more quantum number sets that you can provide that are valid. Keep going. Come up when you're ready. Or tell me.
So it can be, it can be less than 5 even though
Well, iodine has all of kryptons. So you want to spell it out? Here are the electrons that you could give configurations for. Oops, I keep getting this mixed up. That's krypton plus 5s2, 4d10, 5p5. So iodine, yes or no? Iodine has electrons in the first energy shell.
Yes.
How many? 2. So there are 2 quantum number sets that you could provide for the 2 electrons in the first energy shell. How many electrons does iodine have in the second energy shell? In the second shell? 8.
Oh.
2 of them are in the S subshell, 6 are in the P subshell. But it has 8 electrons, 8 different quantum number sets that start with n equals 2. How many in 3? 2, 8, 18. There are 18 quantum number sets that start with n equals 3. So you guys just picked n equals 5, but there is a whole set.
I just want clarification. Each of these 4 numbers describes the configuration of
1
1 electron?
electron. A quantum number set, like Pauli's exclusion principle, says these quantum number sets describe 1 electron. Electron configurations describe all of them with less detail, yeah? The quantum number sets actually give you more specific information. Electron configurations are more broad. If no one's going to come up, I'm happy to dictate. I'll just write it down if...
Can people do it again?
No, let's wait. We've got so many. The potential is endless. So why don't you guys take another 30 seconds, come up with a set that describes any of the 50 remaining electrons.
So we were talking, based on what you said while we were up there, could you do 4, 3? Is that right?
Yes,
Yeah, since
So is your second number?
you could do 4, 3, and then...
what we're doing, because it's 5s and it has 2 electrons, so it has to be 2 minus 1.
well, that's the highest. Yes, it's possible that iodine could have an electron that goes to L equals 4, which I believe is an I orbital. S, P, D, F, G, H, I. But we're going to 4. Anyway, it's a theoretical orbital. All orbitals in the fifth shell, iodine does not have electrons in L equals 4. In the fifth shell, 5s2, 5p5, iodine has electrons in L equals 0 and L equals 1. Iodine doesn't even have electrons in its 5d orbital, let alone its 5f orbital, let alone its 5g orbital. And that's what you were looking at L equals 4 is the g orbital. Does that make sense? So think about this. Pick an electron, any electron. Which one do you want? Maybe you want the 4d10, one of those electrons. N equals 4. L equals 2. That's what D is. D is L equals 2. And then you have the choice of -2, -1, 0, +1. I gave it to you.
Something like that.
Yeah. But I'll spell it out again. We'll go through it. All right, thank you guys. Let's go through and make sure that some of these are valid. And I do want to point out there was one change that was made. Up here, we originally had the set 5, 4, -1, +1/2. Is that a valid set? Yes, it is. Because n minus 1 is 4, and -1 falls between -4 and +4. This is a valid set of quantum numbers, but it does not describe one of iodine's electrons. L equals 4 is not L equals 3, and L equals, I think actually I'll just start from the ground up and I'll explain these 4 primary ones again. When we say an s orbital, we are describing L already. L equals 0. When you describe an f orbital, you are saying L equals 3. So L equals 4 is not one of the principal orbitals that shows up on the periodic table. L equals 4 is a valid quantum set. It is not a quantum set that describes any of the electrons of any of the atoms on the periodic table. Does that make sense? After F, electrons aren't populating. You can get them to populate by exciting them. So I had them change it because despite being a valid set of numbers, it's not a valid set for iodine. So here's what you could have done for any of these. Pick an electron, any electron. I'll pick one of the electrons in the 2p6. N equals 2, L equals 1, because it's p. Now I have the choice of m sub L being -1 to +1, and m sub S being +1/2 or -1/2. How about another one? Oh, that one's kind of boring. So how about this? I want one of these electrons. N equals 4. L equals 2. M sub L can be anywhere from -2 to +2. Does that make sense? The electron configuration tells you which orbitals the electrons are actually in, and the quantum sets have to validate that. So 2 different things. What's a valid quantum set? And what's a valid quantum set for the electrons in this atom or ion? Cool. So let's go through and check. Which energy shell? The 5th. Which subshell? The S, which can only have one answer to m sub L, 0. There's only one s orbital. Spin 1/2. Is this a valid set? Yes, and it describes one of these 2 electrons. I guess I kind of skipped over Ryan and Blake's first one. Which energy shell? 5th. Which subshell? P. Which of the specific P's? The -1 P, one of the 3 possibilities, and it's spin 1/2. So they described one of those 5 electrons. All right, which energy shell? Which subshell type?
F.
F. Does iodine have any electrons in an F subshell? How do you know?
Because the electron configuration doesn't show F.
I wrote the electron configuration. There is no F. If you look at the periodic table, the first time you start filling F electrons is when you have 6s orbitals. You go 6s, 4f, 5d, 6p. 6, 4, 5, 6. So we are not in this shell, or sorry, we're not in this row, we're not in this, we're not able to put electrons here. So is this a valid set for iodine? No, it's not, because there is no F electrons. Deal? We could change it, correct? We could say 5, 2, 5, 1, or 5, 0, but then if we made it 5, 0, we'd also have to change this. Okay. Which energy shell? Second. Which subshell? And only S in there, so we're describing one of these two electrons. Yeah? Which energy shell? Which subshell? Which of them? The -1. Sorry, I should stop asking that question. So what electrons are we answering here? We're describing one of the 10 in the 4d10 electrons. Yeah? 4d. All right. And then lastly, energy shell, subshell. We're describing one of these 6 electrons. And now you've got 47 more to go, right? Okay, that makes sense? Dots are connecting a little bit? Any questions on it?
Helped like thinking like, okay, if you have the quantum numbers, like trying to turn it into the if you take the 4 to negative 1 plus 2 and trying to turn it into the 4 to 10, that was able to help you like.
Yeah, pick an electron from the configuration and describe its quantum numbers, or a valid set, possible. But don't just pick any valid set and see if it describes one. Yeah? Although you could have a question like this where you're given all of these and it says which of these does not describe one of iodine's electrons. And then you need to recognize what's valid and what's not valid for iodine. You may need to quickly jot out iodine's electron configuration so that you can check. Do I have 5s? Do I have 5p? Do I have 5d? Oh, I don't have 5d. I only have 4d. There's an invalid set. Things like that. All right. This takes us into orbital configurations, or orbital diagrams. We're essentially plotting out the energy for these quantum number sets. And this is what you are seeing here on my PowerPoint slide, except that it's upside down. Here, it's filling lowest energy at the top, and then it's actually telling you, come back around and fill 2s before you fill 2p, and then you'll fill 3s before you fill 3p, and then you fill 4s before you fill 3d, 4p, 5s. So that rule I gave you, you're going to fill the 3s after you fill the, you fill the 3d after you fill the 4s, despite 4 being a higher shell number. that actually is accounted for in this little diagram. So this is a screenshot from your book. Draw something out like this, print it out, download it, and just get familiar with that map the first few times you fill. Although I did something with this because its energies are flipped. So I kind of drew it this way, but you can see it's upside down, where you fill 1s, then 2s, then 2p and 3s, because this is how we're going to draw orbital diagrams. So on my left-hand side, an arrow pointing up indicating energy. Along the x-axis, we're not really showing space. We're just distinguishing subshells from each other. So you could think of this x-axis as being subshells. Our first energy level is 1s, which is just one orbital in that subshell. As you move to the next highest energy, you get 2s. Within that shell of energy shell 2, the s subshell and the p subshell are not evenly matched in energy. The p subshell is slightly higher in energy. And notice how there are 3 individual orbitals. This would be -1, 0, +1. L equals 1, m sub L equals -1, 0, +1. And then we fill the second shell. So we move up to the third shell, which we think of as higher in energy than 2p. But in the third shell, we get 3s, 3p, and 3d. Each shell introduces a new subshell type, 3d, which has 5 individual orbitals. L equals 2, m sub L equals -2, -1, 0, +1, +2. And remember, those, very clearly, are the shapes that you're seeing on here. When L equals 0, there is only sphere. When L equals 1, there are 3 orientations. When L equals 2, there are 5 different orientations and shapes that the electron might be found in. Now, if we were looking quantitatively at this, then by the time we get to 4s, we might actually recognize that it's going to fill before 3d. So we may actually want to show that 4s is near the energy of 3d or lower. There's some energetic stabilization that comes here before we see 4p, followed by 4d. And what comes after 4d? 4f, which has 7 individual orbitals, all the way from -3 to +3. But we know that 4f doesn't actually fill sequentially like this. On your periodic table, this is the F block, which means this is 4f. Just like how this is the D block, which means this is 3D. The first D orbital shows up in the third shell, but it fills in the fourth shell. The first F subshell shows up in the fourth shell, but it fills after the 6s. So we know that somewhere between here and here, we're actually filling 5s and 6s before electrons start occupying 4f. So it'd be nice to say that a quantum shell always fills first before other quantum shells, but it's just not true. After you get into these higher energies, the orbitals start misaligning themselves in energy. So the periodic table is actually more effective at helping you figure out an electron configuration than this. But this allows us to merge information about electron configurations and valid quantum sets. We can visually display which of the orbitals is it in. Is it in m sub l equals -1, or is it in m sub l equals 0? And is the electron spin up or spin down? So we still follow Aufbau's principle, which was fill lowest to highest. We still follow the Pauli exclusion principle, which is that no two electrons occupy the same quantum set. And we're going to represent spin up and spin down with these arrows. Spin up, spin down. But you may see them in some places with these half arrows. All the same. All we're saying is plus 1/2, minus 1/2. The distinction between the spins. But now we get this new rule, which is Hund's rule. And I actually remember Hund's rule because it kind of sounds like Hun, like if you've got a honey. That's what Hund's rule is. It's actually forbidding you from having a honey until every orbital within a subshell is half filled. So each orbital half fills before any pairing occurs. You will not have spin up and spin down until every orbital has spin up or spin down. So you have to add in electrons without necessarily knowing, will it have a pair or not? So it's pretty common to just start filling orbitals spin up. The important thing here is whether you fill spin up or spin down, you just have to align all of the spins of unpaired electrons. So all spins align before pairs. I'll give you some examples of reasons that we would need to, or like, give you examples of what that looks like when it's broken. So why don't we take the one that I have and let's fill in electrons for an element. Anybody have an element they want to look at? Great. Okay, we can do sulfur. I was going to pick carbon, but I'm just biased like that. How many electrons for sulfur? 16. If it's neutral, correct? Well, Aufbau principle says I need to start adding those electrons from lowest energy to highest energy. So I'm going to start at the 1s orbital, and I'm going to move up. Hund's rule says I can only half fill an orbital before, or I have to half fill all orbitals in a shell, or a subshell, excuse me, before any of them get paired. And the Pauli exclusion principle says they have to have a pair at some point. They can't all have the same quantum numbers. So I'm going to start here at 1s, one orbital, excuse me, one electron. The orbital is half filled. Now I can give it a Hun, Hund's rule. I pair it, spin down. I've only used up 2 of my electrons. I have 14 more to go. 2s, half filled. Now I go down. 2s2, paired. Now I have 12 electrons to go. I get into the 2p. 1, 2, 3. Each of them are half filled. That's Hund's rule. And their spins are aligned. They're all pointed up. Would it be wrong if they were all pointed down? No. What would be wrong is if you had something like this. 2 that are spin up, 1 that is spin down. This is just not how we find the electrons. They're always aligned before they get their pairs, regardless of what that alignment is. Okay, that's 3 electrons. I'm down to 9. Now I can start giving pairs in the 2p. 1, 2, 3. They're all paired. I've got 6 electrons left. I'm done with the second shell. I fill 3s, spin up, spin down. I fill 3p. I want to make sure I'm keeping track. 3s was 2 electrons. I have 4 electrons left. 1, 2, 3, 4. We mentioned this strange behavior of electrons, that despite being negatively charged particles, they don't always repel each other. They pair. And yet, despite having this stability around pairing, they don't want to pair unless they have to. So notice how we took 1 pair of electrons in 3p and 2 unpaired electrons in 3p, rather than having 2 pairs and 1 empty orbital. There is first an intrinsic stability to having them separate before being paired. It's better to have your electrons more evenly distributed than it is to have them paired with each other. Deal? Spin alignment, Hund's rule. Half fill all of the electron orbitals before you pair any electrons. All right? By the way, this is how I think an atom should be displayed. This would be the quantum mechanics explanation of an atom. We're looking at sulfur, correct? So if we were to go back and look at the Bohr atom, remember Bohr said, Rutherford was right, there's a nucleus and then just clouds of electrons, and Bohr said those electron clouds are at these specific energy levels. This is what Bohr's atom looks like, and I gotta say, I got to visit a biology class, 1610. Anybody take or in 1610? So you maybe have seen this. And I got to visit their class, and they were looking at a chemistry problem. And they said, which of the diagrams below shows atomic number 7 in a positive state through the Bohr model? And I almost threw up. Like, this is not how you should be thinking about atoms. Leave it to a biologist to teach you chemistry in a way that just shouldn't ever be taught. So if this were sulfur and we were trying to show it, here's what we would say. There's an electron here and an electron here. 2 electrons in the first orbital, or the first shell. And then there's 2, 4, 6, 8 in the second shell. 2, 4, 6, 8. And then there's 6 more in the outermost shell. Which of these is conveying more information? The orbital diagram or the Bohr model? Why does the diagram display more information than the Bohr model? Regardless of which one is easier for you to interpret. Yeah? Ryan, you want to add anything? tells you that the electrons are paired. Does the Bohr model tell you that electrons are paired? No, it does not. This tells you subshells. It tells you whether electrons are paired. I guess this is maybe easier to count because if you know it's sulfur, you can just count all the dots to see if it's electrically neutral, negative, or positive. I didn't know people actually said, look at the Bohr model to think about an atom. You shouldn't.
They taught us some of that in chemistry, by the way.
Well, I mean, I covered it too, right? We did say that Bohr
We
proposed
had like,
this.
a test on that.
And then what did I say? I said, gross. Bohr was wrong, and it's okay to be wrong sometimes. I say that because I'm always wrong. Here's what I want you guys to do. I want you to draw the electron orbital diagram for carbon. Feel free to talk with each other. Do your diagrams look the same? How far up do you draw your diagram before you know to stop? You see that?
Oh.
It looks like filling. Yeah. It does not matter whether you start up or down. I have a tendency to do up then down. But even my unpaired ones there are up. But I just noticed somebody that did their unpaired ones down. Does not matter. It does. What's most important is that all spins are aligned before they get pairs. But after they get pairs, it doesn't really matter. And even when they're unpaired, it doesn't really matter whether they spin up or spin down. It's just spinning.
So wait,
But it's not.
if you had, so you showed the example of when it was halfway through the day, the count was different. But if you didn't have it halfway through, would you have a spin up and then spin down? Not pairs and then there's an extra space for it.
Can you say that one more time?
I tried. Is that valid?
No, that's what I crossed out on the
But it's
top.
not all the way through.
All spins must be aligned before pairs. Are there pairs there?
No.
Then all spins must be aligned. There's no pairs in my example.
I thought it had to be like when it had to be halfway full and they had to be aligned.
When they're partially filled, all spins must be aligned. All right. Was this easier or harder than sulfur? It should be easier because you didn't need to draw as many orbitals. Oops, I put 3p, but that's 2p. Carbon is in the second row, so I only need 2s and 2p at most. Carbon has 12 electrons. First I fill 1s2. Did I say 12 electrons? Sorry, 12 atomic mass, 6 electrons. 1s2, 2s2, that's 2, 4, 5, 6. But you could have also done, in the 2p, 5, 6, where their spin are down. They're aligned. That's valid. You could not have done this, where one of them is spin up and one of them is spin down, because before any pairing, their spins must be aligned. But what about this in the 2p? Is M sub L equals -1 higher energy than M sub L equals +1? If it was, we would have drawn them as steps, but they're actually always drawn intentionally, we say degenerate, equal energy. So is this valid? Yes. That's valid. Looks weird, and it's not common to show it that way, but these quantum numbers, whether it's M sub L equals -1 or M sub L equals 0 or M sub L equals +1, aren't so important against each other. It's just that it must be one of them. But which one it is a little bit arbitrary, depending on where you put your axis. All right. I want you guys to take a break, but before you do, here is a meme showing 1s2, 2s2, 2p6, 3s2, 3p6. And I promised a friend of mine that I would show you guys that meme, so this is me fulfilling that contract. You'll notice that those people are trying to do what? They're trying to get in the shade. They're trying to avoid the sun. They're going to the lowest energy available, right? And they're filling from lowest energy to highest energy, just like your electron orbital diagram. All right, why don't we take 5 minutes, get up, move around, get your blood flowing, and then we'll come back in for Module 7. That one's for you, Jonathan.
I missed Wednesday's class, so I am totally lost on the quantum numbers. I get the orbital stuff, but the quantum numbers, I'm like so lost on.
Quantum numbers actually just describe the orbitals.
Oh,
So we've got 4 of them, and you know how to catch up on the videos, right?
Yes.
You can get them on YouTube or on Canvas.
Okay.
N is our first quantum number. It describes the shell. N equals 1, N equals 2, N equals 3.
Okay.
And that roughly correlates with rows on the periodic table.
Okay.
Our second quantum number is L, which is defined by N. L can be anywhere between 0 and N minus 1.
Okay.
So for N equals 1, there's only one valid answer, L equals 0. But for N equals 2, there are 2 answers, L equals 0, L equals 1. And that keeps going up. Those L numbers are what we call the orbitals. S is L equals 0, P is L equals 1, D is L equals 2, F is L equals 3. It goes on, but we don't see electrons occupy anything more than L equals 3. M sub L tells you which specific orbital in a sub-shell of orbitals your electron is in. L equals 1 only has, L equals 0 only has one orbital type.
Yeah.
M sub L equals 0, 0. But L equals 1 has 3 orbital types. M sub L is -1, 0, or +1. So M sub L has defining parameters from L.
Okay.
L has defining parameters from N.
Okay.
And then we get M sub S, which is spin. Is it spin up or spin down?
So how do you know if it's spin up or spin down?
You don't. It's just one or the other.
Cool.
And I don't know if you caught this earlier, but you can think of the electron like a ball spinning, except it's not a ball and it's not spinning. That's
Cool.
that's
Okay.
what spin is.
So like in a real world application, you wouldn't be able to tell.
Actually, I'm glad you brought that up. I'll show a video that kind of explains how they knew what spin was, but
But just by looking at the orbitals and everything, you wouldn't be able to tell which.
No.
There's no way to like.
no, experimentally you can,
Yeah.
but no, from
Just on paper.
just on paper, not really. Except that we say spin up is an arrow
Yeah.
pointing up, and spin down is an arrow
Yeah.
pointing down.
Okay. So you have to like physically look at it to see what the spin is in like if you're applying it.
That's right.
In application.
Yep.
Okay.
Yep.
Cool. Okay. I am still a little bit behind on the homework. I've been focusing on my biology class because I've got
Yeah.
a big test today. So,
Yeah, that's important too.
but it's reinforcing a lot of the chemistry. So it is actually.
I'm glad.
So turns out you need chemistry for biology.
Who would have thought? And why?
But no, it's a lot of the same concepts, just like just turned inside out and upside down.
Exactly. Exactly.
So
Applied, some might say.
yeah, but no, it's good.
If you guys want an exercise, try and determine what element this is. It's neutral, it's not ionic. That would be a trick.
I can't count. Okay.
And that one missing a pair on the right. That is hard to see. I need to replace my orange.
Wait a minute. Well, hi, but Kate, are those both omega? Is one just like uppercase?
Yeah.
I'm not freaking crazy.
Well, I mean, I wouldn't go that far.
Hey.
Look at the difference between pi and pi.
I thought some people were just bad at drawing.
Yeah, me too. Or like the font is different. It is interesting.
Hey, wait. But why do you need an uppercase and lowercase?
I'm not a linguistics major. Why do you need?
My problem is when they switch it.
Are you gonna apply that to all languages or just to those Greek letters you're seeing?
Just to the Greek letters.
Yeah. Why do you need uppercase and lowercase a and b and c?
Well,
C, which doesn't change at all.
yeah.
Why do you call it upper and lowercase? It's just big and small.
Well, that's kind of like in grammar.
Did you even like that tower?
Apply it in math. So what's the difference between an uppercase omega? That bugs me. Why do they switch the pies? Why is
Actually-
one pie for math and one pie's for like the freaking engineering?
Okay, that's a fair question. I've never seen anybody try to write pi as that capital pi on the left.
Really?
But I would say in math, it's even more meaningful to have a larger number of variables. So yeah, I want delta
Okay,
big
just
and
have
small.
them stop using K and X for everything. K is literally everything.
All right, let's.
I thought that the big omega was omega, and then they started using the W omega, and I was like, that's not omega.
Let's solve for this. What element, not ion, is represented on this orbital diagram?
Copper.
Or are you all so confident?
Well, I was, and now I'm not.
So, first of all, I didn't give you any numbers, so you might need to do that first. 1s, 2s, 2p, 3s, 3p, 3d, and 4s. So first of all, this tells me that I can go down to the fourth row of the periodic table, and I can move most of the way through the D block, because I'm in the first time that D orbitals are being occupied. And then all I need is just one less than all 10. Zinc is at the end of the D block. Zinc is our last transition metal. This is not zinc. This is copper. One less. Did that come easily?
Yeah.
Were you able to interpret it? Good. Before we wrap up Module 6, there are a few things that help us kind of segue into Module 7. One is not so helpful, but we call these, well, I'm not sure I know how to spell it, anomalous. There it is. Anomalous electron configurations. There's a couple of families that we pay attention to here. We said that we should fully fill the lowest energy shell or orbital subshell before we move up to the next subshell or the next shell. And then we found that that's not actually true. We start occupying the fourth energy shell with S before we finish the third energy shell with D. And then it turns out it's also not true that we fully fill some shells. There is a stability that comes, and you can ask the atoms why they feel this. There is a stability that comes from having completely half-filled subshells or completely filled subshells. When we look at chromium, and I shouldn't have turned off my periodic table, but chromium is in 3D, so it's in the fourth row, but it's occupying 3D electrons. Chromium has these 24 electrons. If I zoom in on its orbital diagram, just to look at 4s and 3d, of those 24, 18 of them, I think I've got that right, are held in the higher shells. Yeah, 18. So we're just looking at the outermost 6 electrons, the ones that are in 4s and 3d. You would fill this in and expect to find 4s paired and 4d electrons. You would call this 4s2, 3d4. But this is actually not how we find chromium. Instead, we find chromium as 4s1, 3d5. What does it get out of this rearrangement of its electrons? All of the d orbitals, the whole d subshell, will be half filled. And the s subshell is also half filled. So this stability comes from having an entire subshell half filled, even if it means breaking up this small subshells being filled. Better stability. With half-filled subshells. Now there's one other place that this shows up, and it actually comes in copper's family. So this is how you might expect copper to appear, but we're going to zoom in here just on those outermost electrons again. And instead of finding it as 4s2 3d9, we actually find it as 4s1 3d10. 1 electron, 10 electrons. Better stability with a completely filled D subshell plus a half-filled S subshell, as opposed to a completely filled S subshell and a partially completely filled, greater than halfway filled subshell.
So the first incorrect one is the normal E configurations, but the better stability weird one is the anomalous version?
Which is what you would find. Some of you maybe have found periodic tables on the internet that list electron configurations for the atoms. This is what you'll find listed for chromium. This is what you'll find listed for copper. Chromium and copper families, then, are these anomalies. Chromium, molybdenum, tungsten, copper, silver, gold. They fill their electrons more unintuitively than what Hund's rule, Pauli exclusion, and off-ball principles say.
How does that change how they react with things?
Kind of yes and no, but these transition metals, there's an entire class on it in organic chemistry that talks about how and why they change. A property that's still common amongst them is that they all prefer to give up their electrons. So in that way, no, nothing really changes, but there are specific things you can learn about the atoms. For us, we just need to recognize we will preferentially completely half-fill or get something completely filled and completely half-filled. There's better stability in that. These electrons that I've zoomed in on, those that are in the outermost shell, or not necessarily just shell, but the last row of the periodic table, these are sometimes referred to as the valence electrons. And I'm going to give you the best way to think about which electrons are valence electrons for which atoms. Valence, I think I had some students look this up in the past, comes from the Greek meaning strength, or like strong ones. And it's these valence electrons that determine an element's properties. And it's so easy for me to say that these valence electrons are just those in the outermost shell, but it's not always true. Although we do say the valence shell is the outermost shell. But depending on what type of element we're looking at, the valence electrons kind of changes. If we're looking at main group elements, that is S block and P block elements, or it's those columns, 1A, 2A, skip over the D block, 3A through 8A. For main group elements, the valence electrons are in the outermost shell, which means that it will always be in S and P orbitals. So let's start easy, and let's look at carbon. Carbon has 6 electrons. Carbon being in the second row has 2 electrons in the 1s2, and then 4 electrons between 2s2, 2p2. So that means that carbon has 4 valence electrons plus 2, what term can we give them? Those electrons that are not in the outermost shell, those that are in the innermost shell, we'll call them core electrons. So any other element that has 4 valence electrons is going to have similar properties to carbon. Like silicone has 4 valence electrons, similar properties to carbon. But let's take this a step further. Let's look at iodine. We said that iodine has 53 electrons. How many of them are valence electrons? 7. Only those that are in S and P. When you look at the periodic table, iodine is towards the end of a very long row. I'm not counting all of the electrons in that row. Which ones do I count? Only S and P. So for iodine, I'm counting the 5s2, 5p5. I'm skipping over the 3d. This gives me 7 valence electrons, and the remainder are all core, 46 electrons. This includes the 4d10 electrons that show up in the D block. I'm skipping over that D block when I count for iodine. Makes sense? When you're looking at your periodic table, you're not just counting all the way over like you did for carbon. You skip over the you skip over those transition metals. And here it actually works. It actually is true that these valence electrons, just in S and in P, are the outermost electrons. That's the 5s and the 5p, not the 4d. 5s and 5p are the outermost shell. But when you look at transition metals and inner transition metals, just count all those electrons in its row. To be fair, you won't have to guess at some of these because they don't fill, especially when you get to F block, they don't fill one by one by one. You get sometimes these combinations of certain number of electrons in F, certain number of electrons in D. It's not always an even pairing, but you can say it's just this many of valence electrons. So if we look at iron, which appears in the 4th row, but has valence electrons. What? It's not in the 8th row. It's in the 4th row, and it has electrons in both 4s and 3d. We're not counting just s or just 3d, which means we're not technically counting in one shell. We're counting electrons between the third and the fourth shell. But we're just counting all of them. Lizzie, this is what you're trying to give me? And iron has how many total? Based on its periodic, its atomic number? 26 total electrons. Of those, 8 are valence electrons, and the rest, 18, are core electrons. Yeah? Here, notice that we're looking at the 4s2 and the 3d, well, I'm going to have to guess here. I don't have my periodic table pulled up. 3d6. Does that make sense? Depending on where your element is, you've got to consider different shells and orbitals to count all of them. So this is always going to be in the S, in the D, and in the F. You will not find transition metals or intertransition metals with electrons in p orbitals in its valence shell. S, D, and F only. It gets way more complicated. You guys won't have to come across it very much. So I think we're good to move on there. Any questions from you guys? Sarah.
So why doesn't it have the p orbitals? Why does it skip straight to the d?
Well, it's not that it's skipping the p orbitals, but looking at the periodic table, and actually I shouldn't have erased this, but I just had 3d and 4s up here for copper, and we said that it actually behaves like this. I can't say that valence electrons are just those in the outermost shell, because 4 would be the outermost shell. That would claim that copper has 1 valence electron. But actually, copper has 11 valence electrons. I'm counting both the S and the D. Copper doesn't have any in the P. The 4P would fill next. There are none in the 4P. It doesn't have any in F. F doesn't exist yet until we get to the 4th shell, which I know we're in, but we haven't even filled 4P, let alone 4D, let alone 4F. So copper, I count S and D. By the time you're done counting S, F, and D on your periodic table, that's when you get to the P block. And if you're counting electrons in the P block, that's a main group. You're just counting S and P. Should we do one more? What about magnesium? We said magnesium has 12 electrons total. How many of those are valence electrons? Just 2. And what subshell are those in? Those are both S subshell electrons. 2 valence, 10 core. Yeah? So for carbon, we counted both the 2s and 2p. Those are the outermost shell, S and P. For magnesium, we're just counting the 3s because it doesn't have electrons in its 3p. Deal? All right. So in Module 7, we're moving into periodic properties. And again, this is a good segue because the periodicity, the repeating character of all of our elements, it has to do with their valence electrons. Whatever number of valence electrons they have, helps determine their properties. Here's some trends that we see. And we're going to dive into these a little bit more. Metallic character. And being a metal has something to do with how well you can conduct electricity and mainly that. Metallic character increases down a family. What's a family? Yeah, the column, not the row. Like the halogen family is group 7. Oops. The noble gas family, group 8. The chalcogen family, group 6. So let's look at this set of families, or excuse me, this set of elements: oxygen, sulfur, selenium. I always butcher this guy's name. Technetium. These are all in a family. They're all in group 6. Which of these elements might conduct electricity the best? Yeah, technetium. Or however you say it, Te. If you look at your periodic table, I'm not expecting you to memorize this. I expect you to be able to recognize them and find them on the periodic table. Te is at the bottom of that family, towards the bottom anyways. So because we moved down a family, it should have the most metallic character. And which of these is the least metallic? Oxygen. And this actually goes hand in hand. Part of the reason that it is more metallic has something to do with its size. Size increases down a family. So let's consider the alkali metals. Lithium, sodium, potassium. Honestly, I'd rather just keep it with these. Which of these is the largest atom? Potassium. Which of them is the smallest? Lithium. And why is that? Why is the atom growing in size? Keon? It's not because it has more protons and neutrons in the nucleus. Actually, the nucleus stays, we know the nucleus changes in size, but relative to the size of the atom, the nucleus is insignificant. Ashley? The electrons don't pull on the nucleus. When we say atomic size, we're not talking about the nucleus. Good question, though. Sarah? There's more electrons? More shells. That's the predominant feature, is that when you start occupying these higher energy shells, their distance from the nucleus grows. What makes up the size of an atom? Its nucleus or its electron cloud? Its electron cloud makes up the size. So when we say the size is increasing, it is true that the nucleus is increasing down a family, but it's the cloud that is getting larger. Ryan, did you want to add anything to that? Okay. All right, we'll get into some of the other ones. Here I think I actually want to get into our covalent radius. When you hear that word covalent, what other word on the board does it make you think of? Valence. And we said that valence is the electrons in the outermost shell, sometimes. So when we say covalent, what are we saying? Not nearest, with, shared. I like that the most. Like co-pilot, co-parent, coordinate. These are valence electrons that are common between two atoms. They are both utilizing valence electrons. Shared valence electrons. The covalent radius is the size of an atom that we get based on its bonding. And this really works best when two atoms of the same element are bonded to each other. It gets a little bit harder if you've got different elements with different sizes bonded to each other. So let's look at the fluorine-fluorine bond. If we had just fluorine alone, how would we determine its size? It's really hard to gauge how big that cloud is, correct? Where do I make my cutoffs? And I don't know if you guys remember, but we actually said that the cloud, when we draw the orbitals, we're chopping it off at 95% probability. So how do I decide the limit of 95% probability of where that electron is? So instead, we look at a bond between these two atoms, and we measure the radius. Remember that the radius of an atom would stretch from the center of the nucleus out to the edge. So that's R. That's the radius. And how do I decide what that length is? I can look at the distance between the two nuclei. And I can say that R is that distance divided by 2. So I'm reporting the size of an atom, correct? But I'm doing it by measuring the bond length of a molecule and then dividing it in half. So it's not the atom's radius, it's the atom's radius as calculated through a covalent radius. I'm taking a covalent bond, cutting it in half, and saying each atom must make up half of that bond. Works best with with atoms of the same element. So we could go back and prove this thing about size increases down a family by looking at the fluorine-fluorine covalent radius, to the chlorine-chlorine covalent radius, to the bromine-bromine covalent radius, to the iodine-iodine covalent radius, and we could see that that covalent radius continues to increase. The bond length increases divided by 2, that's an increasing radius. But then we find this very strange thing. Across a row, size decreases. The atoms get smaller if they're in the same row. Well, you know that within the same row, you're not occupying larger shells of electrons. But you are still packing more protons into the nucleus and more electrons. So why is the atom shrinking as I add more protons and more electrons? Why is it not increasing? Here we use effective nuclear charge. Which we call ZF. Do you guys remember what Z was back in Unit 2? we had Z and A, where A was the atomic mass and Z is the atomic number. The atomic number is number of protons. So we're taking the number of protons, but we're actually saying, effectively, how many protons do I have? To calculate this, this is an equation. The effective nuclear charge is the atomic number minus the shielding that it experiences. But we can actually replace this shielding with something that we can count and implement on our own. Shielding is to say, all of those protons that are in the core, in the nucleus, they are pulling on electrons. First, they're pulling on the closest electrons. That shields their pull from the next closest electrons, which shields the pull of the protons from the next closest electrons. So we're calculating effectively how much shielding do these protons have. We can swap out shielding with core electrons. So let's look at carbon, nitrogen, oxygen, and fluorine. And let's calculate their ZF for each of these. Wait, question. Does the number of core electrons change across the row? Look at your periodic tables. As I move from carbon to nitrogen to oxygen, am I increasing the number of core electrons? Number of core electrons stays the same. The number of valence electrons is increasing, but the number of core electrons for everything in this row is 2. So I'm going to be subtracting an increasing larger number of protons by the same value, 2. So what is the atomic number of carbon? 6. 6 minus, how many core electrons for carbon? What is 6 minus 2? 4. Carbon essentially has 4 free protons pulling on its outermost electrons. Essentially, 2 of its protons are shielded by the core electrons. What about nitrogen? What is its effective nuclear charge? 5, or sorry, this is atomic number 7 minus 2. Nitrogen essentially has 5 protons that are not being shielded by the core electrons. So nitrogen actually can pull even more strongly on those valence electrons, which shrinks the orbital size. Oxygen, 8 protons minus those 2 core, and fluorine, sorry. This is its effective nuclear charge. Which of them has the strongest charge in its nucleus? Fluorine. So if we look at these atoms, we can draw them as increasingly smaller and smaller electron clouds. And I want to show you the visual that I have for this. It may actually surprise you how little it looks like they move. Oh, and you know what? I might not have even put it on here because I was so upset about it. But here is
a graph that shows their atomic size. And you'll see another one in your textbook if you go and look for it that shows the whole periodic table and their relative sizes. And it doesn't look like they changed that much. But here we go. Here's lithium, beryllium, boron, copper, nitrogen, oxygen, fluorine. I mean, they're all almost the same size, especially compared to these other elements, but there is a change in its atomic radii. So 2 things to consider. How does the size change across the row? How does the size change down a family? Those have 2 opposing trends. All right, we'll pick up with our periodic properties on Wednesday. Have a good night and a good day. I'll see you guys Wednesday.
Thank you.
You're welcome.